G'day and welcome to this video on the semi-log test, which is going to help you potentially with your PSMT. So we're going to talk about a situation where you've collected some data, you've been given some data, and it's exponential, or at least you think it might be exponential. So what we can do is you could take this data, I've got an example here, x, y, y depends on x. We could take this data and we could model it exponentially using either a spreadsheet or Desmos. It's pretty easy to do. But the problem there is that because it's exponential, the data we get back, like the R squared value and things like that, isn't quite as fulfilling. And it's a bit harder to really evaluate how good our data is. So let's have a quick look at what it looks like. I'm going to show a little graph here, okay? And we've got x is 1, 2, 3, 4, 5. Obviously you'd use a ruler. And y starting at, say, 30,000 here. Y is 30,000, 23,000, 18, 15, 13. So we suspect that it follows that sort of model. I've missed all the data points there, but hopefully you get the point. We think it's an exponential model. We know this exponential model is in the form y equals a times b to the power of x, or we could use y equals a times, maybe if we've got some sort of reasonable, suspected base, but then we have to introduce a k, so maybe 0.5 to the power of kx or something. And this will be really useful for later on, but for now, I'm going to stick with this guy here. So the first thing we need to do for a semi-log test is we need to recognise that if we take a log of both sides here, we get a special type of function. And I'm going to show you that over here, and I'm going to have to shift, so my head's just in here, but you can still see the writing, I hope. So we're going to start with y equals a times b to the power of x. I'm going to take a log of both sides, and you can take any base log. Later on we're going to introduce base e, but for now any base will do. So I'm just going to do log of y, and when we do log, remember that log means log base 10. So log of y equals log of a b to the power of x. Now this log of y I'm going to leave it the same, but I'm just going to work on this. Log of a b to the power of x can be split up using our log laws to be log of a plus log of b to the power of x, and then the x can be brought down, so we've got log of a plus log of b to the times x. So the x, the power, can come outside the log, so we've got it as a multiplier there. And if I rearrange this, I get this. I get log of base 10 of b there times x plus log base 10 of a. And this looks a little bit like this. M x plus c. This is a linear function. So by taking a log of both sides, we actually create a linear function. And it's a linear function where we're comparing log y against x. So actually if we graph log y against x, we get a linear function, which is really handy. So what I'm going to do is I'm going to sneak off, clean this a little bit. So if you want to recording this down, then please do now. I'm going to come back and I will have added a log column here. We're going to take a log of all my y values. Give me a second. Okay, so these have magically appeared now. We now have a log y column, and we still have an xy. So the trick here is to recognise that this is exponential, but once we take log of y, this is a linear model. So I can plot this linear model and do a lot of linear modelling. And linear modelling is easier anyway. So what we should have now is if I just drop a little sketch in here, we've got 1, 2, 3, 4, 5 still. And if this is 4, that's 1. Now I've got 4.47, 4.36, 4.26, 4.18 and 4.11. And it's going to be more linear. And I can see that's pretty linear. So what I'm going to do instead, and remember this is technology driven, this PSMT, so I can still do it in technology, is I'm going to go away now and do this linear model on Desmos or on a spreadsheet. And once we get that spreadsheet and Desmos information back, then we'll be able to do something with it. Just give me a second. Okay, so we've got our information now. I've done a linear model. We've got log y against x. We can see it's pretty linear. And this is what I got out of my spreadsheet. So if you want to, you can follow along at home. Do these, get this data on the spreadsheet, do linear models, you get something like this. Note also the R squared value, which hopefully you recognise is a value of how well it fits as a correlation coefficient. It's about 0.98, so it's a good fit. We're pretty comfortable with that. Raw data might not be that good, but even if it's above 0.8, 0.9-ish, we're in a good space, so that's what we're looking for. Anyway, there's my model, but remember, we had this from earlier, so you might want to flick back on the video and have a look at this. We had log y is equal to mx plus c, but actually log y was equal to log of our b value, x plus log of a. So I've just got into the graph there, I apologise about that. So what I'm saying here is that our m value from the linear regression is actually equal to log b. And our c value from the linear regression is actually equal to log a. And a and b are the things we need for our model, because if you remember, our model looks like this. Y is equal to ab to the x. Y is equal to ab to the x. We just need our a and b values. So what I'm going to do is a bit of a rearrangement here. So I know that m equals log base 10 of b. And so by rearranging that, I get b is equal to 10 to the power of m. And similarly, I get c is equal to log base 10 of a. And so therefore, a is equal to 10 to the power of c. Now, I'll pop a little equal sign here, and let's just see if we can dream this into existence. Holy mackerel, here it is. I can't believe I just did that. I really didn't think that would work. Anyway, so we've got b, and our b value is 0.8106. So this is actually good, and I'll explain why in a second. We have our a value is 35514.03. So I'm going to do a little bit of cleaning, and then we'll talk about the results of this. The graph will appear, we'll keep these aside, and then we can talk about what it means. Just give me a second. Wow, here we go. So we've got our b value, our a value, and there's a bit of a graph. Clean it up a little bit. So I want to remind you that we got all this from our semi-log test, which I'll talk about a bit in a minute. But the whole goal here was to get back down to this. Y is equal to a times b to the power of x. So our model now is 35514.03 times 0.816,06 to the power of x. Now I want to explain what this means before we go back to the graph. So remember, first of all, this value, which is our a, well, that was the initial value of the car. And that actually makes sense because you can see here, well, first of all, this value a, that was the initial value. And that makes sense because if we go back to the data, 30,000 was after one time period, whatever that is. Here, 35,514 makes sense as our y-intercept. So we're pretty happy with that. It's about, I don't know, there. Now, it's a little bit lower than I'd expect, but that's okay. We're modelling. It's not an exact situation. And here we have 0.8106, which is, we could say about 81%. So then that means that year on year, or whatever the time period is, the new value is 81% of the old value, which is a loss of 19%. And in the context of what you're doing, that's what we're dealing with, a loss. So we have a depreciating asset. If I go down here, it's going to fit something like maybe this. It might not be perfect, but we don't expect it to be perfect. And you can take some steps to make refinements. For example, you might know the y-intercept, or you might consider whether, if you break this graph up into chunks, there's been a variable depreciation here. There are things you can do to maybe improve your model, but through the semi-log test, we know our R-squared value, and we've got a pretty good idea of what our model is. So just to recap, we start with our data. Now, I would think you'd have more than 5 data points, but you see the space I'm working in. Okay, now we can apply the semi-log test. And it would be good to discuss this if you're putting it into a PSMT. What is it and why are you doing it? Take a log of both, or take a log of our y value, because we're going to model x against log y. By doing that model, we're modelling a linear function. So you build your linear function, and you can do that using technology, and you get your b and a value from that. From your m and c value, remembering that log b is equal to m, and log a is equal to your c, and I did the rearrangement earlier. And then you can put them straight into your exponential model. You have to be considerate, of course, about whether there's a plus d or not. Does that plus D exist, and how are you going to deal with that plus D? So you might need to consider dealing with it before you start this whole modelling process, because it does put things out of whack. So the D is 10,000, I get this model, this D hasn't been accounted for in my modelling. You might want to go back to the algebra, see if you can rebuild that algebra, or you might want to consider, is there a reason or a way you can find the D and take it away from the data before you start the modelling process, because this semi-log test does kind of assume an asymptote at zero. Anyway, if you've made it this far in the video, that gives you a bit of a grounding on a technique that you could use that should help you get a better model and be more reassured that it is a good model. So take this forth. If you want to use it in your PSMT, you're more than welcome to. See you later.